Hey guys, my name is IBM and today I want to take you into the last lesson of quantum physics. I think this is going to be lesson 6. Just to remind ourselves about what we mentioned in lesson 5. In lesson 5 we had introduced the atomic structure and energy levels where we talked about Neil-Bohr's model, and we mentioned that Neil-Bohr just explained what Rutherford failed to explain in his planetary model, where Neil-Bohr has explained that electrons which we would predict to collapse into the nucleus according to the classical theory of electromagnetism. The electrons do not collapse into the nucleus simply because Neil Bohr explained and said they revolve around the nucleus in only certain allowed orbits. And while in these orbits, these electrons do not give out radiation. That's why they don't collapse into the nucleus, as it would be the case as predicted by the electromagnetic theory, which suggested that a charged particle being accelerated around another charged particle would lose energy and then collapse. Then he also went ahead and explained that only electrons give out energy whenever they make a transition. And this transition was specific. Electrons were only making a transition from one specific energy level to another specific energy level. And whenever they made such a lower transition from a higher energy level to a lower energy level, that's when they emitted energy. And this emission led to what we call the line spectrum. So we introduced electron energy levels, and we talked about the ground state of an atom, where we mentioned that this is the lowest energy level of an atom, and we said for hydrogen it is minus 13.6 electron volts. Therefore, it means that an electron in a hydrogen atom in its ground state would require 13.6 electron volts to escape or to completely become free. So we saw that in our previous lesson, and therefore the light emitted by atoms in a solid, atoms in a liquid, or even a gas at high pressure, we mentioned that it produces a continuous spectrum, which could be white light. And when white light is passed through, say, a prism, or it is passed through a diffraction grating, the white light would be split into what we call the 7 colors, or a continuous spectrum with no boundary between them. The reason as to why light produced by atoms in a solid, a liquid, or even a gas at high pressure produces a continuous spectrum of the 7 colors is because of the proximity of the atoms to each other. Atoms in solids, liquids, or even gases at a high pressure are closer together. The interaction between neighboring atoms results into broadening of energy levels, and consequently transitions of a wider range of magnitudes of energy are possible, and light of a broad spread of wavelengths may be emitted. The corresponding spectra will therefore have many different frequencies present, with some even overlaps, and that is what we saw as a continuous spectrum. This part of a continuous spectrum was in an old curriculum called the band theory. That's why I don't want to talk about this broadening of energy levels at this level at this time. However, light which is emitted by solids, liquids, or even gases at high pressure produces a continuous spectrum because um, the atoms are very close to each other, and therefore interaction between neighboring atoms results into the electrons having a wide range of, or occupying a wide range of energy levels. So we say uh, uh, it results into broadening of the electron energy levels. And that means consequently electrons will have a wider transitions. They can undergo so many transitions which are very close to each other, which therefore results into emitting photons of a continuous range of energies, or photons of a continuous range of frequencies and a continuous range of wavelengths, resulting into a continuous spectrum. However, last time we saw that for light, which is going to be emitted by isolated atoms, and I said isolated atoms in this case means they are far away from each other, especially for atoms of a gas at low pressure. The light which is passed through atoms of a gas at low pressure, or the light which is produced in atoms of a gas at low pressure, will not produce a continuous spectrum as we mentioned earlier on. Instead, it will produce what we call a line spectrum. So in this lesson, we are going to distinguish and understand the origin of these line spectra. According to Bohr's model or Bohr's second postulate, electrons only emit electromagnetic radiation, or they give out energy whenever they make a transition from a higher energy level to a lower energy level. And we say this must be electron transition is responsible for these line spectra that we are going to discuss. So the line spectra could either be an absorption line spectrum or an emission line spectrum. In the previous lesson, or lesson 5, we saw an example of a spectra. So let's begin with an absorption spectrum. We mentioned earlier on that when white light passes through a low pressure gas, the spectrum of the white light is then analyzed, and it is found that the light of certain wavelengths is missing. Light of certain wavelengths is missing. So white light is passed through a gas at low pressure, as we saw earlier on. So a beam of white light is passed through a gas at low pressure. And when observed on the screen, some wavelengths are observed to be missing. In their place, instead of having all the wavelengths which make up white light ranging from violet to red, some positions where we would expect these wavelengths to be, we would see dark lines. So in their position, we would see dark lines as shown here. So this spectrum is what we call an absorption spectrum. When white light is passed through a low pressure gas, and the spectrum is analyzed, this could be passed through a diffraction grating. If the white light is passed through a diffraction grating, as we saw in lesson 5, then what is seen on the screen is not going to be a continuous range of the 7 colors. Within the 7 colors, we see dark lines as shown in this diagram. And this is what we call the absorption spectrum. And this is an example of absorption spectrum. Now the question is, why do we see this absorption spectrum? That's what we want to understand. Remember, if the gas was a gas at high pressure, that means the atoms are very close. And I mentioned when I was starting this lesson that when the atoms are very close, it means the electrons in these many atoms will have now a wide range of energies because of the interatomic forces between these atoms which are very close. The forces between different atoms affect the energies which can be occupied by the electrons, which therefore means electrons can have a wide range of transitions possible because of the proximity. So that is possible for a gas at high pressure, a solid, and a liquid where the atoms are very close. But for a gas at low pressure, the atoms behave as if they are far away from each other, they are isolated, therefore the interatomic forces are negligible. So an atom behaves as if it is isolated, and therefore the electrons within that atom do not experience forces from any neighboring atom. So when these electrons undergo transition, the electrons behave as if they are individual electrons because they don't experience a lot of interference from neighboring atoms. And therefore, when electrons undergo transition, when the light is analyzed, some of the wavelengths are going to be missing. Now the question is, which wavelengths are missing and why are they missing? So in their place, we see dark lines. In the place where we would expect the wavelengths to be, those missing wavelengths are represented by dark lines as shown by this diagram here. And I'm saying this type of spectrum is what we call the absorption spectrum. How do we come up with this absorption spectrum? So as the white light passes through the gas, some electrons absorb energy. Remember last time in lesson 5 we saw that the energy which causes transition must be equal to the difference between two energy levels. The energy which makes transition is equal to the difference between two energy levels. So as the white light passes through the gas, some electrons absorb energy. It is those photons whose energy is equivalent to the energy between the two possible energy levels of the electron in the atom that are absorbed. And when that photon is absorbed, the electron makes a transition to higher energy levels. Remember, when an electron makes a transition to higher energy levels, as we saw in lesson 5, I mentioned that the atom is in an excited state. And therefore, it doesn't stay there for long. So the wavelengths of the light that the wavelength of the light they absorb corresponds exactly to the energies needed to make that particular upward transition. So a photon, or if this is an electron within an atom, and let's just represent this with as the second the higher energy level. So when a photon with the right amount of energy, which is equivalent to the difference between two energy levels, is absorbed, then the electron is going to be promoted from that lower energy level, maybe if that was its ground state, to a higher energy level. And we say an upward transition has taken place. Of course, that's an absorption. Unfortunately, when this electron tends to, of course, the atom is unstable, and in the process of trying to gain stability, the electron must lose the energy it has acquired. However, when the electron loses the energy it has acquired, the energy it has acquired may not be emitted in the same incident direction as before. Initially, the photon was moving in that direction, but there is no guarantee that it's going to be emitted in the same direction. It is emitted randomly, so it could be emitted in this other direction. Which means if you had several beams or several photons incident in that direction, this photon which has been emitted randomly in this direction will not be seen on the screen because it will not emerge, because during the excitation, the electron emitted a photon randomly in a different direction. Such a photon will not appear on the screen, and in its position you will find there a dark line. So when these excited electrons return to the lower levels, the photons are emitted in all directions randomly, rather than in the original direction of the white light. Thus, some photons or some wavelengths appear to be missing, resulting into dark lines on a white background. So if you have a white background, you may find the 7 colors could be there, but within the 7 colors, you would just see dark lines. So these wavelengths will appear to be missing, resulting into dark lines on a white background. This is what we are going to call an absorption spectrum. So basically, an absorption spectrum is a band of dark lines on a bright or a white background, or bright background, or dark lines on a colored background. That's what we call an absorption spectrum. And how does it come about? White light, which is passed through a gas at low pressure. White light which is passed through a gas at low pressure, when analyzed, it will not emerge on the screen as when analyzed may be passed through a diffraction grating. It may not appear on the screen as a continuous beam of the 7 colors or a continuous spectrum. Within the spectrum, we may find there within the spectrum, let's say of a bright screen, we may find there dark lines. And I'm saying the reason is very simple. When white light goes through the gas, some photons have a specific amount of energy needed by electrons within atoms to be to be promoted to higher energy levels, which makes the atoms to be excited. On electron excitation, when the electrons de-excite, they must emit these photons to move back to the ground state. But the emission of these photons is random, and the photons are emitted randomly in all directions. So these photons may not have followed the same path, but instead may have been re-emitted in different paths. And these wavelengths, or the wavelengths correspond to these photons, may not appear on the screen. And where the wavelengths are supposed to be we would see dark lines on a bright background, or dark lines on a white background. And that's what we are calling an absorption spectrum. So let's just have a simple comparison so that people understand the difference between a continuous spectrum and an absorption spectrum. So it therefore follows that the wavelengths missing from an absorption spectrum are actually going to be those present in the emission spectrum of the same element. So if the wavelengths missing when light goes through hydrogen are, let's say, A and B and C, these are the wavelengths which are missing when light goes through a hydrogen. These are going to form an absorption spectrum. And if light goes through light goes through hydrogen, and we form what we are going to call an emission spectrum, these are the wavelengths which will be present, because an absorption spectrum is formed on a darker background. They are going to be dark lines, and an emission spectrum is going to be formed on an absorption spectrum is formed as dark lines on a bright background, and an emission spectrum is going to be formed as bright lines on a dark background. So the continuous spectrum, if there was no such a scenario of wavelength missing, we would expect such a scenario. And I say this is possible for light from atoms of solids, liquids, and gases at high pressure, where the atoms are very close and the electrons have a wide range of energy transitions due to the proximity of the atoms and due to the interatomic forces between different atoms within the material. But when an absorption spectrum is emitted, this is what we expect. Within the continuous spectrum, we have dark lines. And the same dark lines would be represented with the bright lines if an emission spectrum is emitted. So notice the difference between an absorption spectrum. These are dark lines on a bright background, and an emission spectrum are going to be bright lines on a dark background. And where we have the darker lines in an absorption spectrum of the same element is where we expect bright lines on an emission spectrum of the same element. Let's say the element here was hydrogen. So in summary, when someone talks about an emission spectrum, we are referring to the colored lines which are superimposed on a dark background. Colored lines superimposed on a dark background. And when we talk about an absorption line spectra, we are referring to dark lines superimposed on a continuous spectrum, or dark lines on a bright background. Dark lines on a bright background. Superimposed on a continuous spectrum, or dark lines on a bright background. The bright background could be continuous spectrum, but within the spectrum, we see the dark lines. So that is the difference. However, both line spectra and both absorption and emission spectra, these ones are as a result of electron transitions. These are as a result of electron transitions. So those are what we call the emission and line spectra. So to fully understand this, I have just mentioned that when when an atom or when an electron absorbs a photon, it makes a transition. And it is only the right photon which is going to be absorbed. For example, let's say we have two photons. We have this one and this one here. So this one just continues, it is not absorbed because its energy is not enough to promote an electron from a certain energy level, from one energy level to another. If this is a hydrogen, the energy of this photon is not enough to promote the electron from its ground state, say from negative 13.6 to negative 3.4. So this photon is not going to be absorbed. It is a photon whose energy, the energy of a photon should be equal to the difference between two energy levels. Between two energy levels, which if this is E1 and this is E2, it should be the difference between two energy levels, which will be E2 minus E1. So if this photon's energy is not equal to the difference between two energy levels, it is not absorbed. So we know that white light consists of photons of many different wavelengths ranging from red, which is approximately 700 nanometers, to violet, which is approximately 400 nanometers. So within this range, there are so many wavelengths, so many wavelengths. So only specific photons have the energy required to promote electrons in a given material from one energy level to another energy level. And different electrons in different atoms require photons of different energies. So you may find that a photon which promotes an electron um, from a lower energy level to higher energy level in hydrogen may not be having enough energy to promote to promote an electron in, say, argon from a lower energy level to a higher energy level. So each material has its own line spectrum. Each material has its own line spectra because these line spectra are characteristic of the material. That's why astronomers are able to know that there is, let's say, there is helium and hydrogen around stars simply because the line spectra formed in light coming from those stars is the same line spectra which is formed when light is passed through hydrogen or helium in the laboratory. So astronomers can now know what element makes up something or what the element could be by looking at the line spectrum. So for a photon to be absorbed, it must have exactly the right energy to lift an electron from one energy level to another. If its energy is too little or too great, it will not be absorbed. Remember, the photon does not share its energy among electrons according to what we saw in our photoelectric effect. So it is always a one-to-one interaction. So a photon whose energy is too little or it is too great cannot be absorbed by the electron, so it does not excite the atom. Okay, so to fully distinguish between an emission line spectra and an absorption line spectra, I'll just consider these simple diagrams which I drew. So let's think of light being emitted and passed through a gas at low pressure. When this light is passed through this system, of course, the system is just going to be acting as an analyzing system. And what we are interested in is when it is passed through a prism. Is it going to be split into the 7 colors, or is it going to form an absorption or an emission spectra? So when light is passed through a hydrogen gas or is passed through gas at low pressure, we mentioned that for low pressure, um, an emission line spectra can be observed by passing light emitted from a heated gas at low pressure in a discharge tube through a spectroscope. So a spectroscope, this arrangement here is going to be called a spectroscope. Of course, we don't need to know what a spectroscope is in more details. So the light is going to be separated into different frequencies or wavelengths by a prism and brought to focus on different sections of a white screen by lenses. So the light is brought to focus on different sections of of a white screen by lenses. And in total darkness, if we create darkness around here, in total darkness, the screen will show colored bright lines, which are actually the images of the rectangular slits through which the light passes. Of course, here just considered one slit. So in total darkness, the screen will show colored bright lines, which are actually the images of the rectangular slits through which the light passes. So an emission spectrum is simply colored bright lines. Colored bright lines. The best way to see these colored bright lines is if we are in total darkness or if they are projected on a dark screen. Note very carefully that different elements, as I mentioned before, have different configurations of energy levels. And therefore, in a discharge tube at low pressure, electrons in their excited states fall back to lower energy levels by emitting photons of specific frequencies or wavelengths seen as lines on the spectrum. So electrons in their excited states, of course, they have to make lower transitions, that is by emitting photons. And they also, because they absorb specific frequencies or specific wavelengths or specific energies, then they also make specific transitions by emitting specific frequencies to move back to lower energy levels. And in the process of moving back to lower energy levels, then they emit these photons, which are going to be seen as bright lines on a darker background. So in simple terms, the lines appear to be bright on a dark background. So in a nutshell, what I'm saying is that an emission line spectrum, if it is emission, for an emission line spectrum, they must appear as bright lines on a darker background. That's why we need a total darkness to be able to see these lines. Bright lines on a dark background. Now, what is very important is that when you look at this spectrum on the screen, you notice that the lines are going to be separated. They are not overlapping. The lines are separated, which gives evidence that the energy levels of the atoms are also separated. The reason as to why there is a space between the line spectra formed is because the energy levels are also separated. In other words, the energy levels are discrete. They do not overlap. Electrons only make specific transitions. The energy levels are separate. The energy levels are discrete. These lines can be viewed, the lines can be viewed through diffraction grating, and this provides useful information for scientists to identify elements and study their atomic structure. So scientists can study elements in different objects, elements in stars, and so on and so forth by using these lines. And I mentioned that if an element produces these lines in the same position, then it can be identified to be the same element. For example, if light from the stars is analyzed and we see the position of the lines, and we produce light, we pass light through a similar element, or we pass light through an element in the laboratory, and the lines are produced in the same positions as light from the stars, then we can conclude that the element we are testing in the laboratory is the same element in the stars. That's how scientists are able to tell that around the stars there is helium and hydrogen. So the description I've just given above, or from the above description, we can see that atoms of a given element, say helium, can only emit or absorb light of certain wavelengths. And I've just mentioned that different elements emit and absorb different wavelengths. They emit and absorb photons of different energies. So the question is, how can this be? But to understand this, we need to establish two important points. One of them, we mentioned it in lesson 2, if not lesson 3. As with the photoelectric effect, we are dealing with light. Of course, light is an electromagnetic wave, but is interacting with matter. Hence, we need to consider light as consisting of photons. What do we know about photons? Remember that for light of a single wavelength and a frequency, the energy of a photon was given as, I think, hf. So for light of a single frequency, single wavelength, the energy of each photon is given by the equation energy is equal to hf or hc over lambda. So because we are dealing with light, and light has a range of wavelengths, That means each photon has its own frequency, or each photon has a wavelength. So it means a single line may be corresponding to a single wavelength, or a single photon, a single frequency, and therefore a single wavelength. Secondly, you should also notice that when light interacts with matter, it is the electrons that absorb the energy from the incoming photons. So the electrons absorb energy and make a transition. When the electrons lose the energy, light is emitted by matter in the form of photons. So electrons absorb the energy and make transitions, and electrons lose the energy to make another transition, but in the opposite direction. These transitions are responsible for the line spectra. Okay, briefly, I also want to talk about the absorption spectrum to distinguish it from the emission spectrum. In the same way, when we pass light through a gas, this time it is a cool gas. The other one was heated gas. Of course, heated gas is at high pressure. Cool gas, cool gas is going to be at low pressure. So when light is passed through cool gas and passed through a spectroscope, then when light is analyzed on the screen, what is formed is going to be different from what we saw previously. Remember, for an emission spectrum, it was bright lines on a dark background. But in this case, when light goes through a gas at low pressure, that is cool gas, instead of an emission spectrum, a line spectra is produced. So absorption line spectra are produced when white light from an incandescent lamp passes through a container of cool gas. What happens is that electrons from the ground state in the cool gas absorb some photons, as we mentioned earlier on, and they transit to the excited states. So we say the electrons get excited, or the electrons move to higher energy levels, and the atoms get excited. An atom's energy can change by only a discrete amount. In other words, electrons can only absorb specific amounts of energies or specific photons which are able to promote these electrons to higher energy levels. And we mentioned earlier on that if the energy of the photon is not enough to promote an electron to another allowed energy level, that photon is not absorbed. If a photon energy is just enough to excite the atom such that an electron can jump to one of the higher energy levels, I mentioned that that photon will be absorbed. That is, electron transition is going to happen. An electron only absorbs a photon of the correct energy to allow it to make a transition to a higher energy level. And this means the atom is going to be excited. But earlier on, we mentioned that an atom cannot stay in an excited state for a long period of time. It must gain stability by making the electron to shed off this energy. So the intensity of the incident radiation is reduced since it has lost a photon. Then, because it has lost a photon, a darker line on a white background is going to be observed, whose wavelength or frequency is that of the photon which has been absorbed. Remember earlier on I mentioned that this photon could be re-emitted, but the re-emission may not be in the same direction in which it was moving before. It may be, initially white light may be moving in that direction, and white light has all these photons. And when white light goes through the gas, some of the photons are absorbed. And when these photons are re-emitted on de-excitation, the photon may not be emitted in the same original direction, but may be emitted randomly in another direction. So I'm saying the darker line would be corresponding to this position, to the position where this photon would be missing. Therefore, I want us to note that the continuous spectrum obtained on the screen would be having some missing frequencies due to the absorption of photons by the cool gas. And therefore, These missing photons would appear as darker lines superimposed on a bright colored background, or darker lines on a continuous bright background, or darker lines superimposed in a continuous spectrum, and we just call it an absorption line spectrum. So now we know the difference between an absorption line spectrum and an emission line spectrum. For an emission line spectrum, we have bright lines on a darker background. And for an absorption spectrum, we have darker lines on a bright background. So the absorption line spectra are found when the light from stars like the sun is analyzed, and the interior or the central core of the star is considered to be very hot, and we know that it emits white light of wavelengths in the visible range ranging from red up to violet. However, when this light is analyzed, we notice that there are lines. This is because the light has to pass through cooler outer layers of the sun. I think the cooler layer of the sun is called the chromosphere. Because the chromosphere is cool, that means the pressure is low. It means the atoms of the gas around that area are relatively far away from each other. Therefore, they behave as if they are isolated. And therefore, when light goes through them, instead of producing a continuous spectrum, we expect a line spectrum uh, because of the less interference between the atoms. It means the broadening of energy levels of electrons cannot occur. So electrons will have specific transitions possible, which results into specific energy levels, which results into the line spectra that we have mentioned. So as a result, certain frequencies or wavelengths are absorbed, and this results into what we call the line spectra. In conclusion, on one end I demonstrated the absorption spectrum. On the other end, I demonstrated the emission spectrum. So electron transitions from a lower energy level to a higher energy level results into what we call an absorption spectrum. So these lines are pointing upwards because the photons are emitted. Of course, that's where we stop seeing the photons, but they could be re-emitted randomly in all directions. So normally a photon is absorbed before an electron can transit up to a higher energy state. And this normally produces what we call an absorption spectrum. And an absorption spectrum are simply darker lines on a white or colored background, dark lines on a bright background. That is an absorption spectrum. On the other hand, when electrons make a transition from a higher energy level to a lower energy level and the photons are emitted in their right direction, on the screen where these photons are emitted by light, this results into what we call an emission spectrum, and which is going to be bright lines as we see on a darker background. And you notice that the position of the bright lines is the same as the position of the dark lines because the element is the same. The element is the same. So when an emission spectrum is produced by the same element, the bright lines are formed in the same position where the darker lines would be produced if an absorption spectrum is emitted. Do not forget that atoms of different elements have different line spectra because they have different spacings between their atom energy levels. They don't have the same energy levels because of how tightly these electrons are bound to the atoms, to the nucleus, and how close the atoms are in a given material, and how many, depending on also how many electrons are within the atoms. Different elements have different line spectra. That's how we are able to distinguish between hydrogen, helium, argon, and so on and so forth. So the reason as to why they have different spacings is of course beyond the scope of this syllabus. So in a nutshell, we have tried to distinguish or to compare the emission spectrum with the absorption spectrum, and you should have an idea about the emission spectrum and the absorption spectrum. Question. So here is a simple question. What does the appearance of the line spectra tell us about electrons in atoms? Why do we see lines in a given spectrum? Why do we see the darker lines, or why do we see the bright lines? In other words, what does the appearance of the line spectra tell us about electrons in atoms? So we notice that these lines tell us that electrons can only absorb or even emit photons of certain energies. Electrons can only absorb or even emit photons of certain energies. Because electrons can only absorb or even emit photons of certain energies, it means only electrons in atoms have specific energy levels they can occupy. Therefore, they have specific or they have discrete values of energies. And if this energy is not what the photon has, then the electron will not absorb it, because it means it will not be able to be promoted from one energy level to another. And an electron also will just make a transition from a specific energy level, if it is a higher energy level, to a specific lower energy level, and therefore will give out a photon of a specific amount of energy, which is equal to the difference between the two energy levels. Therefore, we are saying the appearance of the line spectra tells us that electrons can only absorb or emit photons of certain energies, not all ranges of energies. And from this, we can therefore deduce or conclude that electrons in atoms can themselves only have certain discrete values of energy, specific energies, specific energy levels. Electrons can only absorb or emit photons of specific energies, which means they only have certain fixed discrete values of energy. And of course, we earlier on saw that an electron in a hydrogen atom can have only one of these values of energy and not um, an intermediate between these two energy levels. It cannot have energies between the energy levels. So an electron in a hydrogen atom can have an energy between can have minus 13.6, it can have 3.4, but cannot have any value between minus 13.6 and minus 3.4. So electrons have specific energy levels in atoms. They only absorb specific energies and therefore have specific energy levels. Examples. So calculate the wavelength of the radiation emitted when the electron in a hydrogen atom makes a transition from the energy level minus 0.54 times 10 to the power of minus 18 joules to minus 2.1 times 10 to the power of minus 18 joules. They have given us Planck's constant, they have given us the speed. Of course, remember we mentioned that for a photon to make a transition, the energy of the photon should be, or for the photon to cause transition, the energy of a photon should be equal to the difference between two energy levels. This energy level is higher than this one, so I'll call this one E1, and I'll call this one E2. A transition, the electron is making a transition from a higher energy level to a lower energy level. So the difference in energy is of course always going to be the highest minus the lowest. So the the photon energy, because we want the wavelength of the radiation, and we know that the wavelength can be got from the energy is equal to HF, which is going to be equal to HC divided by the wavelength, and the difference in energy is going to be equal to, okay, I'll make lambda the subject, so lambda is going to be equal to Hc divided by the difference in energy. So this implies that wavelength is going to be H, which is 6.63 times 10 to the power of minus 34, then times C, which is 3 times 10 to the power of 8, divided by the difference in energy is going to be this is going to be minus 0.54 minus negative 2.18. This is times 10 to the power of minus 18. So we subtract, the first minus is subtracting, then the second minus is the negative energy. Remember, we mentioned that all the energies are negative because the force between the electron and the nucleus is always attractive. That means moving an electron and yet energy at infinity is 0. So that means if the force between the electron and the nucleus is attractive and yet energy at infinity is 0 and maximum, it means in between there the energy is less than 0. That's why they have negative values. So the work done to take, so energy is added to the electron to take it to infinity, and energy is removed from the electron to bring it from infinity. So the energy is always going to be negative. So I'll press my calculator. Okay, so from the calculator, I'm getting 1.21 times 10 to the power of minus 7 meters. Of course, when I divide this by 10 to the power of minus 9, I think it is 121 nanometers. So I think this answer is correct. Then part B, the energy of the ground state of a mercury atom is E1 equals to minus 10.4 electron volts. On a scale in which an electron is completely free of the atom is at 0 energy. Calculate the ionization potential of the mercury atom. Okay, so of course at infinity energy is 0. That means the ionization potential is going to be the difference in the energy, or the energy required for the electron to be completely free, which is going to be the difference in energy. So this is going to be the energy at infinity minus the energy E1, which is going to be at infinity the energy is 0 minus E1 is negative 10.4. So 0 minus negative 10.4, that is 10.4 electron volts. So this is going to be the ionization potential. Okay. The first four energy levels of a hydrogen atom are shown below. This is going to be besides. What is the ionization energy of the hydrogen atom? What is the ionization energy of the hydrogen atom? Of course, to find the ionization energy, I'm going to just find the difference. So the ionization energy is going to be simply the difference. Of course, for the electron to be completely free, that's when we have the ionization energy. If the ground state is minus 13.6 electron volts, it means the ionization energy is going to be the energy at infinity when the electron is completely free minus the energy E1. So this is going to be 0 at infinity minus negative 13.6 electron volts, which is 13.6 electron volts. When an electron is given 13.6 electron volts, it will be completely free. What is the minimum frequency of the photon that is required to cause an electron in the ground state of the hydrogen atom to be ionized? The minimum frequency. Now that we have the ionization energy, remember the difference in energy is going to be H times F. So it means F is going to be equal to this energy divided by H, which means this is going to be equal to, the energy is 13.6. Because it is in electron volts, I will change it to joules by multiplying this by 1.6 times 10 to the power of minus 19. Then I divide this by Planck's constant, which is 6.63 times 10 to the power of minus 34. So I'll just check with my calculator. So from my calculator, 13.6 times 1.6 times 10 to the power of minus 19 divided by 6.3 times 10 to the power of minus 34. So the answer is 3.3 times 10 to the power of 15 hertz. That is the frequency. What would likely happen to photons of energies 12.75 and 15.0 electron volts if they pass through the gaseous hydrogen atoms in the ground state? So let's check. What does 12.75 do? So minus 13.6 plus 12.75. If it doesn't promote it to any of the energy levels, that photon is not going to be absorbed. So let's check. Minus 13.6 plus 12.75. This gives us negative 0.85 electron volts. It means that photon that photon is going to be absorbed and it will cause that transition. Then let's check 15.0. So minus 13.6 plus 15.0. This is minus 13.6 plus 15. So this is 1.4. It will not cause any of the transitions there, so that photon is not going to be absorbed. So the photon of 12.75 electron volts is going to be absorbed because it's going to cause a transition up to minus 0.85 electron volts. But the photon of 15.0 electron volts is not going to be absorbed because it does not fit in any of the available energies. Okay. Bombarding electrons of energies 5.0 electron volts and 11.0 electron volts collide with the gaseous hydrogen atoms in the ground state. How much energy is absorbed by the gaseous hydrogen atoms, electrons in the ground state? So first of all, we have to check and see if the energy makes a transition. First of all, I will start with 5.0. So we have negative 13.6 plus 5.0. This is going to give us minus 13.6 plus 5 minus 8.6. We don't see minus 8.6 here, so this one will not be absorbed. The question is how much energy is absorbed by the gaseous hydrogen atom electrons. So for this one, it is 0. It is going to be 0. So it means no energy is absorbed by the electron at the ground state from this photon. Let's check the next one. Negative 13.6 plus 11.0. So 13 minus 13.6 plus 11.0. This is negative 2.6. And when you look at this, we don't see negative 2.6 here. So this is also not going to be absorbed because it will not cause any transition, because remember it is only photons whose energy, bombarding electrons of energy is 5. Okay, it's only electrons. It's only the right amount of energy which is going to be absorbed. This energy does not cause any promotion. This energy does not cause any promotion. So it means bombarding electrons, the bombarding electrons do not have enough energy to promote the electrons of hydrogen to a specific energy levels. Remember, only specific energy levels exist in a hydrogen atom or in atoms, and therefore specific amounts of energy are required to promote our electrons to high energy level. So in both cases, we see this results into minus 8.6, this results into minus 2.6, and we don't see that those transitions here. We don't see minus 2.6, we don't see minus 8.6, therefore these transitions are not possible. So in the first case, the bombarding electrons do not have enough energy to raise the electron in the hydrogen atom to the next level. Hence, no energy is going to be absorbed at the ground state. And for the second one, also the bombarding electron would retain most of its energy as it passes through the hydrogen atom because it will not be absorbed. So how much energy is retained by the bombarding electrons? So we say they are not absorbed, so they will retain all their energy. Just like if photons had lower energy, if the energy of the photons would not promote electrons to a specific energy level, they wouldn't be absorbed, so they would retain their energy. Then part E. If a hydrogen atom is in the energy level n equals to 3, show all the possible transitions that the electrons can undergo on the diagram and find the corresponding frequencies of the photons that are emitted or absorbed during the transition. Or maybe just to take you back onto part D, since we use the bombarding electrons, yet for photons, I think this is going to be different from photons because for photons, their energy exists in packets and remains as packets and is absorbed as packets. Since we are using bombarding electrons, perhaps the first one, its energy would cause minus 8.6, and minus 8.6 is somewhere in between here. So this will not be absorbed. It will remain with all its energy. But for 11.0, it is causing minus 2.6. That is minus 13.6 plus 11 is minus 2.6. And we are noticing that minus 2.6 is somewhere in between here, minus 2.6. That means um, there's a possibility of uh, the electron giving out its energy. What is the difference between minus 13.6 minus negative 3.4? This is going to be equal to 10.2. So it means the electron may lose 10.2 to promote the ground electron to this energy level. Therefore, it remains with a balance of 11 minus minus 10.2, which is 0.8. So if we use 11.0 electron volts, this bombarding electron may give out 10.2 electron volts to the hydrogen electron, to the electron in a hydrogen atom, so that this electron is transferred or makes a transition to E2. And then the bombarding electron may remain with 0.8 electron volts. Yeah, so I think for the first one, because we are using bombarding electrons, for the first one, because its energy does not promote the electron to any or even above the next energy levels, it is not going to be absorbed, so it remains with all its energy. For 11.0, because its energy is higher than its energy when absorbed by the electron, if it was to be absorbed, is higher, but because only possible transitions are possible, only specific transitions are possible, the hydrogen electron is going to absorb only 10.2 from the bombarding electron, and the balance is going to remain with the bombarding electron. If it was photons, photons would not completely be absorbed because for them, it is emitted as packets, it travels as packets, and is absorbed as packets. If a photon had 11.0 electron volts, which does not fall on any of these energy levels, the photon would just continue on its way because it doesn't give out part of its energy. It is absorbed as a whole and it ceases to exist. But for bombarding electrons, these ones can give out some of their energy and they lose some and they remain with a very little amount of energy. And the electron, which is in a hydrogen atom, will only take away the specific amount of energy required to promote to the next energy level. So for the second one, 10.2 electron volts is absorbed and 0.8 is going to remain. Okay, if a hydrogen atom is in the energy level n equals to 3, show all the possible transitions that the electron can undergo on the diagram and find the corresponding frequencies of the photons that are emitted or are absorbed during the transitions. So I will change the color here to green. So the electron is at n equals to 3, where this is going to be n equals to 3. So possible transitions. So it is possible transitions that the electron can undergo on the diagram and find the corresponding frequencies of the photons that are emitted or absorbed during the transition. So if it is at n equals to 3, to gain stability, the photon can give out all its energy to the ground state, or it can give out all its energy to the first excited state. But remember, in this state, this is also unstable, so it can also undergo further transition to this energy state here. So that is very possible. So we can find those energies. For the first one, I'll call this one, because they want us to find the corresponding frequencies. So I'll call this one F1. So we know that energy of a photon, H times F, is equal to the difference in the energy levels. So I'll say F1 is going to be equal to the difference in the energy levels is minus, the highest energy level is minus 1.5, so it is going to be negative 1.5 minus negative 13.6. This is an electron volt, so I'll say times 1.6 times 10 to the power of minus 19. Divide this by the Planck's constant, that is 6.63 times 10 to the power of minus 34. I'm just making F the subject in this formula, difference in energy divided by Planck's constant. So this is giving me 2.9 times 10 to the power of 15 Hertz. I'll call this frequency F2. So F2 is going to be the energy difference is minus 1.5 minus negative 3.4. This is multiplied by 10 to the power of 1.6, because I have to change it from electron volts to joules. So it is times 1.6 times 10 to the power of minus 19 divided by Planck's constant 6.63 times 10 to the power of minus 34, which is so this is 2.5 times 10 to the power of 15 Hertz. Then the last one is F3. F3, I will just press my calculator. Difference in energies is minus 3.4 minus, so this is F3. Minus 3.4 minus 13.6 times 1.6 exponent minus 19 divided by Planck's constant 6.63 exponent minus 34. So F3 is going to be equal to 4.6 times 10 to the power of 14. So you notice that the transition from the third to, actually this would have been called, I would have called this one F31. This I would call it F32 from second to the third. This I would call it F21. F31, that is from the third to the first. F32 from the third to the second. F21 from the second to the first, or to the ground state. You notice that the bigger the change, the bigger the transition, the higher the difference in energy, and the higher the frequency, because the energy is directly proportional to the frequency. Okay, I think that is fine. And I even gave answers here. I think we got that answer. We saw that minimum frequency, and I gave an explanation here, but I used the simplest, that if we check the ground state minus 13.6 when we add 12.75, it gives us negative 0.85. That means we can make a transition by adding this energy. We make a transition to negative 0.85, and I say the photon disappears as its energy is absorbed by the electron. Remember, the photon energy is absorbed as a whole. The photon will pass through the atom without being absorbed. That is for 15. 15 electron volts is high enough, but doesn't promote the electron to any energy level, so it's not absorbed. And I say this was different for a bombarding electron. There's a difference between the photon and the bombarding electron. The difference is that for a photon, it is either absorbed or it is not. For a bombarding electron, it can lose its energy, but the electron of the hydrogen only absorbs the required amount of energy. We saw that for 5.0 it was less to promote it to go even to a higher energy level, so it wasn't absorbed. And yet for 11.0 electron volts, it was higher, so the electron in the hydrogen atom would only absorb 10.2, because 10.2 plus 13.6 would promote this to negative 3.4 electron volts, which means there would be this electron would remain with a balance of 0.8 electron volts. And we have also calculated these energy transitions from E3. They said draw. We always draw the energy transitions using the vertical lines. And I think I've calculated that. You can also verify. The diagram shows some of the energy levels of hydrogen. Calculate the wavelength of the emitted electrons when the electron initially in n equals to 2 makes a transition to the ground state. So n equals to 2 makes a transition to the ground state. So the difference in energy is equal to HF, which is Hc divided by wavelength. So they want us to calculate the wavelength of the emitted electrons. No, this can't be emitted electrons. That should be wavelength of the emitted photons. Wavelength of the emitted photons. When the electron initially in n equals to 2 makes a transition to the ground state, in which part of the spectrum does it lie? So wavelength is going to be, the difference in energy is going to be minus 13.4 minus negative 13.6. I have to change it to electron volts, to joules. That is times 1.6 times 10 to the power of minus 19 divided by, I'm making lambda the subject. So lambda is, no, that's not true. If I make lambda the subject, it is Hc over energy difference. So it is going to be 6.63 times 10 to the power of negative 34 times 3 times 10 to the power of 8 divided by energy difference, which is minus 3.4 minus negative 13.6, then times 1.6 times 10 to the power of minus 19. So I'll check with my calculator. So this is giving me 1.22 times 10 to the power of minus 7 in meters. So in which wavelength, in which range? Remember, Reed's mother is visiting Uncle Xavier's garden. In the visible range, we have 10 to the power of minus This is 7 times 10 to the power of minus 7 for red. Then for violet on the right hand side, violet is 4 times 10 to the power of minus 7 meters in wavelength. So 1.22 times 10 to the power of minus 7 meters, I think it is on the left of the right hand side of the visible spectrum. Because the power of 10 is minus 7, but is just less than 4, then this is going to be ultraviolet. So I think that is ultraviolet region. If the atom in the ground state absorbs 1.936 times 10 to the power of minus 18 joules, to what level does the electron make a transition? So let me change this to electron volts. So this is going to be 1.936 times 10 to the power of minus 18 divided by 1.6 times 10 to the power of minus 19. I'm changing it to electron volts, 1.963 exponent minus 18 divided by 1.6 exponent minus 19. So this is the values here are to 3 significant figures. I will take it as 12 point, let me take 12.3 electron volts. So they said if the atom in the ground state absorbs 1.936 times 10 to the power of minus 18, I think I pressed the calculator wrongly here. This is 1.936 times 10 to the power of minus 18 divided by 1.6. So this is 12.1. 12.1. So remember the atom is in the ground state, so it means we have minus 13.6 in the ground state plus 12.1, and I think this is going to be minus negative 1.5 electron volts. So the question is to what level does the electron make a transition? Of course, we notice that the new energy after absorption is this. The new energy is going to be that, and therefore it is going to jump from the ground state to this state here. So it is going to be from n equals to 1 to n equals to what? 3. Okay, so this makes a transition. The new energy after absorption is minus 1.5 electron volts, and therefore it jumps from the ground state up to n equals to 3. The diagram shows some of the energy levels of hydrogen. Calculate the ionization energy and the speed of the electron. Okay, so for ionization energy, we consider infinity and the ground state. So the ionization energy is going to be the difference in the energy, which is the energy at infinity minus the energy at n equals to 1, which is 0 minus negative 13.6 electron volts, which is going to be 13.6 electron volts. So that is the ionization energy. And the speed of the electron, which could just cause the hydrogen atom to be ionized. So if this is the ionization energy, then maybe this energy goes to the electron as the kinetic energy. So if this energy becomes kinetic, I have mv squared is going to be equal to this ionization energy, which is 13.6 times 1.6 times 10 to the power of minus 19. So I'm just going to make v the subject as the square root of 2 times 13.6 times 1.6 times 10 to the power of minus 19 divided by the mass of the electron, which is 9.11 times 10 to the power of minus 31. I'll just check my calculator and see if the answer is correct. Okay, so depending on what you use as the mass, if you use 9.11, you may get 2.18. What is very important is the first three significant figures is the same. When you use 9.1, which is normally quoted in the list of constants, you may get this. If you use 9.11, you may get 2.18, and this digit may be different, but the power of 10 is the same. Okay. So recall that ionization energy is the energy required by an electron to move from the ground state out of the atom to infinity in that case. Of course, you will not be asked to define ionization energy, but of course that energy which is going to be required to completely make the electron free is what we are going to call the ionization energy. The figure below shows some of the energy levels of neon. Determine the wavelength of the radiation emitted in an electron. In an electron transition from E4 to E3. E4 to E3. We want to determine the wavelength. So energy or difference in energy is equal to Hc divided by the wavelength. So the wavelength is going to be equal to Hc divided by the difference in energy. So this is going to be 6.63 times 10 to the power of minus 34, then times C, which is 3 times 10 to the power of 8, divided by the energy difference is minus 0.81 minus negative 2.77, but this should be times 1.6 times 10 to the power of minus 19 to change it to joules. So from my calculator, I have 6.3 times 10 to the power of minus 7 meters. So I think that is correct. This should be the last example. The figure shows one of the energy levels of neon atom. Capture the wavelength of radiation emitted when there is a transition from E3 to E2. So this is almost the same question from E3 to E2. So wavelength is going to be Hc divided by the difference in energy. So that is 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the difference in energy, which is minus 2.77 minus negative 4.87. Then I change this to joules, that is times 1.6 times 10 to the power of minus 19. So this is giving me 5.9 times 10 to the power of minus 7 meters, which means this is correct. Okay, I think you now qualify to do some self-check. You can always pause the video and try to check and see if you can get the answers. So calculate the wavelength of the radiation emitted when the electron in the hydrogen atom makes a transition from minus 3.4 times 10 to the power of minus 19 joules and minus 8.5 times 10 to the power of minus 18 joules. They have said use Planck's constant as this and the speed of light as that. The electron in a hydrogen atom makes a transition from the energy level minus 13.58 to the level 13.58 electron volts when a photon is absorbed. Calculate the frequency of the radiation absorbed. I think sorry, this should be negative 3.4, not negative. So it's negative 3.48 electron volts, not it's not negative 13.5. I mean not 13 point, because remember all the energies are negative. So that is negative. That is a typing error. Negative 3.48. Actually, not 3.48. It's negative 3.38 because we want it to round off to negative 3.4. So it's negative 3.38. Okay. So that is just a correction, because the energies are supposed to all be negative. It can't be positive. So this is negative 3.38 electron volts. So you can check that. The energy to completely remove an electron in the ground state from an atom is called the ionization energy. This energy must be supplied by absorption of a proton, in which case the process is called photoionization. Use information from the figure below to deduce the wavelength of the wavelength of radiation required to achieve photoionization of hydrogen. So they've given us Planck's constant as this. Speed is that. Remember, in the exam, Planck's constant is quoted as 6.63 times 10 to the power of minus 34 joule seconds. So it's better you always get used to using that. So this is what they have given us. So you should be able to find, they said we are going to calculate to deduce the wavelength of radiation required to achieve photoionization, that is from the ground state to infinity. So from the ground state to infinity where energy is zero. So that you just need to find that what? You just need to find the wavelength. Of course, the wavelength is equal to hc over the difference in energy. But of course, the difference in energy is going to be just positive 13.6. So I think that one is a direct question. The figure below shows part of the energy level diagram of an imaginary atom. It is imaginary. The arrow represents 3 transitions between the energy levels for these transitions. For each of these transitions, capture the energy of the photon. So energy is just the difference. That one I will not do. Capture the frequency and the wavelength. Because if you have the energy of the transition, then energy is equal to hf, which is hc over lambda. So you could be able to find that. State whether the transition contributes to an emission or an absorption spectrum. So from this, from a higher energy level to a lower energy level, I think that is an emission. And from a lower energy level to a higher energy level involves an absorption. I think that one is direct. The figure besides shows another energy level diagram. In this case, energies are given in electron volts. From the list below, state which energies could be absorbed by such an atom. We have 6.0. So we just need to check by maybe adding onto n of the energies available to see if there's a possible transition involved, or there is a possible transition with these energies. So the first one is 6.0. We can check. When I add 6.0 here on minus 47, so 6.0 plus minus 47 plus 6.0, I don't get any of the energies above, so this is not going to be absorbed. When I add 9 to minus 47, let me check. 9 minus 47 plus 9 minus 38. Minus 38 is between minus 47 and minus 22, so this is also not going to be absorbed. Set from the list, state which photon energies could be absorbed by such an atom. Oh, by the way, I could also have added 6 to minus 22. So when I add 6 here, let me check. 6 here minus 22 plus 6, it gives me minus 16. Minus 13 plus 6, it gives me minus 7. Of course, I can't add minus 4 plus 6 to get anything. So I have to check again with the 9. Minus 47 plus 9, it doesn't give us. Let's say minus 22 plus 9, it gives us minus 13. So when I minus 22 plus 9 gives us minus 13. So this one is absorbed. Then minus 13 plus 9, I think it gives us minus 4. So it means minus 9 is absorbed. Let's check 11. Minus 47 plus 11 minus 36. Minus 22 plus 11 is minus 11. Minus 13 plus 11 is minus 2, which is this transition here. So this one is, that transition is possible if I add plus 11. So this is also going to be absorbed. You can check 20. Minus 47 plus 20. I think that is minus 17. Minus 47 plus 20 minus 27. I can check minus 22 plus 20 is minus 2. That means this can be absorbed. The transition is possible from minus 22 to minus 2, so that is absorbed. I will check 25. Minus 47 plus 25 is minus 22, so this is possible. So it means this can also be absorbed. Then 34, minus 47 plus 34 minus 13, so this is also possible. That transition is possible, so this can be absorbed. Then 45, we have minus, why did I say minus 20 is absorbed? Did I say minus 47 plus 20? Then minus 22 minus 22 plus 20. Yeah, that was possible. Then 45 minus 47, of course, plus 45, that is 2. From minus 47 up to that, that is possible. So it's like all the energies can be absorbed apart from 6 electron volts. 20 electron volts has a corresponding difference between energy levels. So this was, I think this is a mistake, because 20 plus minus 22, I get minus 2. So it is only 6 electron volts which cannot be absorbed. Therefore, all the energies will be absorbed apart from 6 electron volts, because if these are energies of photons, the energy of the photon should be able to promote the electron to a specific required energy level. And lastly, you can try out this one. The line spectra for a particular type of atom is found to include the following wavelengths: 83, 50, 25. Capture the corresponding photon energies in electron volts. Of course, if we have those wavelengths, energy is equal to H times C divided by wavelength. So that one is direct. Sketch the energy levels which could give rise to these photons. On the diagram, indicate the corresponding electron transitions possible for these three spectral lines. So you're going to be able to draw such transitions. Many times they will give you a scale, or they will give you the energy levels in the horizontal as horizontal. Because the line, it says sketch the energy levels which could give rise to these photons. On the diagram, indicate the electron transitions responsible for these three spectral lines. So if these are the energy levels, maybe this is, which one is 15? Okay, let this be the 49. 15.0 electron volts is the energy of the photon. So let me check which one is that one. So negative 59.7 plus 15. So this one is 15.0. From this energy level to this one, it requires 15.0 electron volts. Then this one, I think this should be 24.9. I'll check. Minus 59.7 plus 24.9. Then the other one is 49.7. So this is 49.7. Now notice that these arrows can also point upwards. It is also the transition is also possible to be in this opposite direction, so this would also be accepted. Of course, the scale would be given, and it's up to you to draw these lines, and the vertical lines indicate the transitions. I think that would be enough for quantum physics. Do not forget to watch the solved past paper questions. They will give you the best picture of what the examiner is looking for. Until next time, bye bye.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. Life lessons come one in a dozen. The other 11 give something from nothing. I sit here looking for an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. One day I'll be yours. One day I'll be yours. I'll be yours. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 give something from nothing. Life lessons come one in a dozen. The other 11 get something from nothing. Life changes, just open the door. One thing certain, I'll always be